let's finalize the plan for final exam. I wanted to give the people who don't come to class another choice essentially to come in and like voice their opinions. But I guess they are fine either way. So, as far as I remember, the idea was I will open the exam from Thanksgiving, from the week before Thanksgiving. So essentially November 22nd, right? Before.
Right after. I thought we did the week right after.
Right after Thanksgiving? Okay. Yeah. Okay, so I'm gonna open the exam to you guys just after Thanksgiving, the week after Thanksgiving. So on Monday after Thanksgiving. Okay. Cyber Monday. So and I will keep it open until the scheduled day of the final exam. Okay? You will have like 3 hours, 2.5 hours to essentially submit your answers. Okay? We can do more. We can do like 5 hours. But it depends. I have to design the exam and see how it goes. But I'm gonna give you like the book problems. I will ask you some like questions, like define this, define that, explain a physics phenomena, and so on and so forth. Okay. So, is there any objections or questions or opinions?
I thought we were going to do like a take-home style, just because the problems sometimes take a really long time.
Okay.
But that's up to you.
How much time were you thinking? I remember it was an open discussion. We didn't decide on it.
I guess maybe like a day after you download it, like what we did for flight dynamics.
I think we talked about 24 hours.
24 hours. Okay, that works for me. As long as you guys don't cheat. I guess hopefully you won't cheat, man. And I will try to. I will make sure to like have all of your grades ready before opening the final exam.
And can you post the homework solutions?
Yes. I have all the solutions. Everything is ready to go. It's just I haven't posted it yet. This semester has been I was just talking to Anna, Victoria, and Nanda with the COVID situation, and then I had this personal things happening to me. It was an awful semester. I just can't wait for it to finish. So it is done then. I'm going to, let me give you a time slot. I am going to post the lecture on November 29th. Okay? And you are going to have access to it. I'm not sure what is the scheduled final exam day is on. Is it 14th?
It was the very last day of the last.
It should be 11th then because I think the final exam day, the last exam day is December 11th. So, but I will check that and send you an email. Okay. And yeah, so it will be open and it will be as soon as you start working on the exam, you will have 24 hours to submit it. Don't work on it together, work separately, and don't cheat, please. Of course, let me put this way, whenever you guys cheat, like, not whenever, like 50%, 60% of the time, I figure it out. Not just me, every one of your other professors figure it out as well, because we have been students too, right? We have cheated too. So, and but we usually don't do anything about it, but yeah. So keep that in mind. I guess that's it. Is there any questions? So let's begin the discussion on chapter 11, and you can of course ask any questions, and if any question came to your mind. in the middle of the lecture as well. The chapter 11, we are going to talk about two connected but separate parts. We are going to talk about the component matching and off-design analysis. We will have an introduction to what the off-design analysis is, and then we will talk about the engine component matching, and we will talk about the off-design analysis itself. And the last part are the unchoked nozzles and the engine performance testing. I expect to finish this chapter in 2 sessions. So this lecture and the next lecture will probably spend like half a session like solving an example. And then we will move on to rockets. So the main question we want to answer in this chapter is how does an existing engine behave in an off-design operating conditions? But before that, we have to answer this: what may cause this off-design condition? There are a couple of things that may cause an off-design operating condition. Altitude, which may include non-standard ambient pressure and temperature. For example, Arctic flight and seasonal effects. Flight Mach number from takeoff, climb, cruise, dash, approach, and landing. Throttle settings, which is the turbine entry temperature. The afterburner settings, whether it's off or on, or is it partially on or off. So all of these different parameters here may cause an off-design operating condition. Also, the nozzle area ratio, which is usually used to optimize the installed thrust, changing that area ratio may cause an off-design operating condition as well. Okay? So, to be able to figure out how we can deal with an off-design operating condition, we just have to talk about the engine component matching. Right? We have to be able to match each part of the engine by itself. We have to be able to match the turbine to the compressor to the burner, turbine to the nozzle, and turbine to the burner or the combustor. Right? Which is essentially the same. It is a different approach to what we have already done before. We already usually did the marching technique, right? So we started from one place, we went to another place. But the thing is, right now we are going to focus on the limiting parameters, like what limits the compressor turbine as far as it is related to what limits the compressor's operation as far as it is related to turbine. Like how does turbine limit the compressor's operation, right? So that's essentially what the engine component matching is focused on. And what you want to do, as we always do when you are dealing with an aerodynamic analysis, external, internal, or fluid mechanics analysis in a more general perspective, is that we have to write the physical laws that govern a fluid flow, right? So the first question we want to answer is that what are these physical laws that need to be satisfied by the engine components that interact with each other regardless of their mode of operation. So we have a set of physical laws that have to be true no matter the operating condition, the mode of condition. Is it mode of operation? Is it design parameter? Is it design operating condition or off design operating condition? It doesn't matter, right? These sets of laws have to be satisfied. And what are those laws?
Continuity, momentum, energy.
Exactly. Conservation of mass, the momentum equation, and the energy equation. So, in order to find the component matching equation, you essentially have to use 3 sets of laws and go forward. But in this chapter, I try to focus less on the proof of these equations and more of the equations themselves and the concepts, right? Okay. Is there any questions so far? Before talking about the component matching, we want to talk about the corrected parameters a little bit. So we define this corrected mass flow rate and the corrected shaft speed and two other corrected parameters in an engine, mainly because we want to normalize or standardize the engine calculations. So what you do is that you define a corrected pressure, which is the ratio of the pressure at each stage, total pressure, with a reference pressure, and a corrected temperature, which is theta I, the ratio of the total temperature at each stage divided by a reference temperature. Usually these reference temperatures are sea level conditions, right? But you can use whatever you want to use. I would assume all of us will use the sea level conditions because all of the tables, all of the references you want to use are derived based on the sea level conditions. Okay. So with these two parameters, two new parameters that we have defined, which is going to be your corrected pressure and the corrected temperature, or pressure correction ratio, something like that. We can call it different names. We can actually define a corrected mass flow rate, which we usually show with M dot C I. And this I is referring to each state. So we can have M dot C 0, M dot C 1, M dot C 2, M dot C 3, right? And that is defined as M dot I multiplied by the square root of your theta I divided by delta I. You plug the definitions in, and you already know how to calculate M dot I. So we can just plug the equation in and find an equation for the corrected mass flow rate as a function of reference pressure and temperature, as well as the Mach numbers and gamma. Okay. I just want to make sure that we are on the same page here. This I here refers to the stages. So we can have delta at the engine face, which is going to be the compressor inlet, so delta 2, right? We can have a delta at the turbine inlet, which is going to be delta 4, right? And so on and so forth. Does that make sense? So this I changes based on the station you're looking at. And the shaft RPM, the engine shaft RPM, is actually, or the shaft speed, we usually use the corrected shaft speed as well for the normalization purpose as well. N of CI is defined as N divided by the square root of theta I, and theta is your corrected temperature. We also define M dot F, so fuel mass flow rate, the corrected fuel mass flow rate, using this equation. And keep in mind that when you're dealing with a jet engine, M dot F only enters at one station. So we don't have M dot Fs at different stations. And we make that correction usually using the corrected pressure and temperature at the engine face, which is the compressor inlet. Okay? And we also have the corrected thrust, which is your thrust divided by your pressure ratio, the ambient pressure, corrected pressure, ambient corrected pressure, and the TSFC, which is your regular TSFC divided by the square root of theta naught. Okay, actually play with this equation a little bit, because this is a pressure ratio by, this is a temperature ratio by itself, right? You can play with this equation a little bit and find the corrected TSFC as a function of your phi of D multiplied by M dot FC divided by your corrected thrust. Is there any questions so far? No? Okay. So next step, let's talk about the component matching. The first component we want to match is the inlet and the compressor. Okay. So the idea was we want to write the conservation equations, right? To essentially find the relationship between the inlet and the compressor. The first conservation, so for most of these, we are only going to use the conservation of mass equation to find the relationship. We are not going to use the other ones, right? So conservation of mass, essentially, we have to find the mass flow rate and set the mass flow rate at the inlet equal to the mass flow rate of the compressor. The general formula for the mass flow rate is this. And something that you have to keep in mind is that we have actually made this formula a little more general than we have already seen. And that's essentially by the inclusion of M of Z. This is telling us that the flight, we are only talking about the mass number in the actual direction. We don't care about the other components of Mach number here, or the flow velocity here, but we are acknowledging the fact that they may be present, right? Does that make sense? Okay, so for the station 2, we can write the m dot, which is essentially going to be the same equation. The only difference is going to be that we are going to use the total pressure, total temperature, and the Mach number, the actual Mach numbers I'm making for the station 2. And for station 0, m dot naught, we're going to write the same equation. The idea is, based on the conservation of mass, these two must be equal, right? Pretty simple. So you set them to be equal to each other. So what can we find from this equality? It's essentially we can find the unknown of the problem is usually phi of d. The rest of it is usually known. Or whatever unknown you have, right? You have one equation that's going to help you find an unknown. As you can see, these are new equations or new concepts. It's just a different, newer approach to the problem, right? So, getting a grasp, you just have to make sure you understand the perspective. Right? The equations are essentially the same equation. The idea, conservation of mass, right? You have been hearing about conservation of mass for a long, long time, right? So it's the same idea. Any questions so far? So we are going to march through engine, and the next thing we want to talk about is the compressor-combustor matching. So for compressor-combustor matching, if you write the conservation of mass, your m dot 4 is going to be equal to m dot 3 plus m dot f in your combustor. So that whatever mass coming into the combustor from the compressor plus your fuel flow rate, fuel mass flow rate. We can actually divide everything by m naught and include the f in our calculation. So m dot 4 is going to be equal to 1 plus f. M dot naught, which is itself equal to 1 plus f m dot 2. You have to keep in mind that we here in this type of off-design analysis, we are usually assuming that fuel-to-air ratio is set by the trial or the pilot. So we are assuming it is a known parameter, right? Now, actually, this is one of the things that may make it a little clearer, make the difference between what we are doing right now and what we did before a little clearer. So here we are dealing with a generator that is already designed and in operation, right? We are not trying to design an optimized engine with an optimized fuel-to-air ratio, right? We are dealing with that. So based on this tank that is already in operation, F becomes a known parameter. You don't need to calculate F, right? Does that make sense? Just if you put more if you put more pressure on the gas pedal, which you don't have, but if you had a gas pedal, if you put more pressure in on the gas pedal, you're going to get more more fuel rate, fuel mass. I'm sorry. Okay. So we are going to apply the same equation, the main equation we had from the previous slide for this to the station 4. Your m dot 4 is going to be equal to the square root of gamma t over RT multiplied by the rest of it, which is the total pressure, the square root of total temperature. We have seen this equation many, many times now. Okay? And we can find the PT4 as a function of PT naught using the pressure ratios that we have seen. Okay? And we already have we already have the equation for m dot 3. We already have the equation for m dot 2 and m dot 3, which essentially has to be equal. So what we do, just give me 1 second, guys. Just started hurting a lot. I'm sorry. Oh. Okay. So we have this equation, right? M dot 4, which is going to be your combustor exit. We also have m dot 2 from the previous slide, which is your compressor inlet. Based on the conservation equation, these two must be equal. Conservation of mass equation, these two must be equal. PT4, we have this equation for PT4. You just replace that here. We can also find the PT2 from the m dot 2 equation as a function of PT naught, right? Like that here, we simplify everything. Everything here, just the only thing that you have to keep in mind is that your gamma for m dot 4 is different from the gamma of the compressor, the cool part of the engine, the cold part of the engine. So we are going to have an equation that relates the combustor to the compressor. And based on this equation, we can draw a performance map for the combustor and compressor and their relationship essentially. We can draw a performance map that gives us the m dot, the corrected m dot at the engine phase. That gives us actually a pi of c, the compressor pressure ratio, as a function of corrected m dot at the engine phase, right? Based on that, you're going to have this performance map, and which you're going to have the constant throttle lines for everything. It's a complicated map. I just wanted to show it to you here. Based on this performance map, you can essentially very simply find the off-design parameter you're looking for. Just come to this map for a specific m dot c2, you can find the pi of c you're looking for. Does it make sense? Okay. So the goal here in an off-design analysis is to essentially find these performance maps for each of the components. Okay. The next thing we want to talk about is the combustor and turbine matching. The steady-state combustor turbine interaction is dominated by the choked turbine nozzle. So that's the first assumption you are making, that the turbine nozzle is always choked. And the turbine cooling requirements is also a very important factor here. Hot spots in the turbine entry plays an important role, and loss of turbine efficiency due to cooling plays an important role in the interaction between the combustor and the turbine. our goal in the turbine off-design analysis is primarily to calculate the turbine expansion parameter, which is essentially its power production capability, right? We have a schematic of a turbine, two different turbines, one an uncooled turbine and the other one is a cooled turbine. So for an uncooled turbine, we can have two different corrected mass flow rates. We can calculate two corrected mass flow rates at the inlet and the outlet of the turbine. And we can actually find the ratio, find the corrected mass flow rate ratios by the pressure ratio of the turbine divided by the square root of temperature ratio of the turbine. And this is pretty simple to get to, right? To find this ratio, you essentially divide these two equations, m.4 and m.5 must be equal based on the conservation of mass law, so they cancel out. And you have theta, delta, theta 5, delta 5, which are the ratios with the reference temperature and pressures, which are also the same for these two, so they cancel out as well. The only thing that remains is going to be the total pressure ratio for the exit and the outlet and the inlet of the turbine, and the total temperature ratio for the outlet and the inlet of the turbine. So you end up with this equation. And we're going to see later on why this equation is an important. This is not just a random equation, but we're going to see later on why is this important. So what would happen to our analysis if we have cooling? Or how could we model the effect of cooling on turbine aerodynamics? What do you think? What is going to happen to the m.5, let's say, or m.4? What is going to happen to m.4? The first thing you need to answer here is that look at here. So the main principle you're going to have when you're dealing with the cooling is that you're going to get some air from the compressor, right, to cool everything down. Does it make sense? Okay. So essentially, you are going to get some air from the colder part of the engine to cool the turbine down. What's going to happen to your m.4? It is going to be lower, exactly. And it's going to be lower.
M.C would be lower. M.4 would be the same.
M.4 itself will be lower because it's essentially you are using different pipes, right, to get the same amount of air. It's a little hard for me to draw with my left hand, but so the idea here is that there is some mass coming in. You're taking some of it right here. So this m.5 is going to be equal to m.2, but m.4 here is going to be different than m.2 and m.5 because some of the mass is going to pass through another pipe. Yes.
And here we're not talking about bypass, right? This is different than a bypass.
Like the concept is not different, right? We are essentially dividing the mass, right? But the purpose is to cool down the turbine. So that's the turbine cooling. Does it make sense?
But it's not like the bypass there, it's a bypass in the actual.
Exactly. It is. This is happening inside the engine, is inside the gas generator. The goal of the bypass is not to cool down the Okay, so using this new formula for the cold turbine, you can actually find this corrected ratio as well. You can find the new corrected ratio. And that epsilon 1 and epsilon 2 is essentially going to present there if only you have different channels for turbine cooling, right? So you always have to be mindful. If you have 2 channels for turbine cooling, you will have 3 epsilons, right? This epsilon is a fraction of the mass that is going to, I don't want to use the word bypass, but it is essentially bypassing your turbine, right? Is there any questions so far? Okay. The other thing we always have to talk about, and it is another important part of the important relationship inside the gas cylinder, is the component matching between the compressor and turbine. So compressor and turbine. So compressor and turbine, we don't really care about when you're matching these two components of the engine. You don't really care about the conservation of mass anymore. What we care about is the energy equation, right? Because the turbine is going to transfer some energy to the compressor, right? So we are going to use the energy equation to find the matching relationship between these two. Essentially, the shaft power is going to remain the same between the two, or we can find the compressor power, which is this amount of energy input that compressor, it's the amount of energy that compressor can transfer to air, right? This can be calculated by the total enthalpy at station 3 and station 2, the compressor outlet and compressor inlet, total enthalpy of air multiplied by the m dot naught, that's for the compressor, and that has to be equal to mechanical efficiency, which refers to the losses you're going to have inside the shaft because of the presence of gears and so on and so forth, multiplied by the turbine power, right? And the turbine power itself is essentially going to be equal to HD4 minus HD5 of the air multiplied by m dot naught plus m dot f. Okay. We have seen this equation many times before, right? And we also have seen this variation of the same equation, right? We actually, I think we proved it in one of the lectures that if you divide it by the enthalpy HT naught, and if you divide it by one of the temperatures, this is the equation you're going to get. This is essentially the same equation, just a different variation of the same equation, right? So that's the energy equation between the turbine, the energy balance between the turbine and the compressor, but represented in the form of temperature ratio, the compressor temperature ratio and the turbine temperature ratio. It can be proved that this turbine temperature ratio is going to stay constant for different operating conditions, for different off-design, for a wide range of off-design operating conditions, right? So if we keep this tau of t constant, what is going to change here? What is going to... So one of the things that is definitely changing is your compressor temperature ratio, right? The off-design parameter is going to change a lot of things about compressor, right? What else is changing? CPs are not changing, F is not changing because that's a known parameter. That's our input, that's the pilot's input. That's actually Joshua's input, right? And the mechanical efficiencies are not going to change. That's an assumption. What is going to change? That's it. That's the only thing that is remaining, right? So the ratio of your compressor temperature ratio for an off-design condition is all the refers to the off-design condition minus 1 divided by your design condition temperature ratio minus 1 is essentially equal to the temperature ratio for that same parameter. But we also have, we have already seen the relationship between the compressor pressure ratio and compressor temperature ratio before, based on the polytropic efficiencies and all of those equations that we have already seen, right? So we can actually find this relationship for the pressure ratio of the off-design operating condition as a function of temperature ratio of the design condition, right? And the ratio of the two temperatures for the off-design condition and the design condition. Does this make sense? Because we already had this equation, and we have seen these two equations from chapter 4. We are just essentially plugging this into this equation. Okay. So this equation is telling us, using the component that compressor turbine component matching, you can actually find the compressor pressure ratio of an off-design operating condition using the temperature ratio of that off-design operating condition. That's the temperature after the combustor and before the compressor. And the rest of it, you're supposed to have the rest of it as design condition. You are the one who have designed it. We can actually show that the shaft speed is also follows the same pattern. So the shaft speed, this is the corrected shaft speed for an off-design condition divided by the shaft speed of the design condition is also a function of that temperature ratio. The only difference is that we are going to have a square root here. The proof of this is in your book, so if you are really interested in seeing that proof, please refer to your book and find them. And we can also find the ratio of the corrected m dot for the off-design condition divided by the corrected m dot of the design condition as a function of compressor pressure ratio for the off-design design condition and the shaft speed here. And just replace the shaft speed with this equation. So, using these three main equations, we can actually find the performance map of the compressor and the turbine as a function of your how far away you are from your design parameter. This is usually called the percent design. This percent design is how far away you are from the operating condition. And yeah. Is there any questions so far? Okay. So let's talk a little bit about the pumping characteristics. The pumping characteristics is actually refers to the characteristics that you are dealing with when you are dealing with an existing gas generator. So we have an on-paper aircraft engine, which is a design part, which is something that is not in operating condition, for which you have to find a performance map. But we usually deal with the existing gas generator, for which someone has already found the performance maps and everything else, right? When dealing with these existing gas generators, you want to find the pumping characteristics, which are the following. These are called the pumping characteristics. You want to find the corrected airflow, and let's see C2, you want to find the pressure ratio of the gas generator. That's the PT5 divided by PT2. The temperature ratio of the gas generator, that's the PT5 divided by PT2. And the fuel flow parameter, or the corrected fuel flow rate. These four are called the pumping characteristics. So if you were asked to find the pumping characteristic using the performance map or whatever, these are the four that you want to find. And usually when you're dealing with an existing gas generator and someone asks you to find something that is already flying, you usually go back and find the pumping characteristics, right? You don't go, because the performance maps and everything else are already available to you. The equations you are going to use are essentially going to be the same equation that we have already seen many, many times. But one small note here that we want to talk about, like some small interesting equations that we want to talk about here, are hidden in these equations that I have listed here. So the first equation, n dot C2, relates your n dot C2, which is your engine phase flow rate, the corrected engine phase flow rate, to the n dot C4, which is the corrected flow rate at the face of the turbine, right? And we've already seen the equations. We can also rewrite this equation as a function of pi of c. So this tells you that you can find the compressor ratio as a function of these two m dots. Okay, is there any question so far up until here? It's just a very simple equation. We have seen this before. It's just a different variation of it, right? Which can help you calculate m dot C2 and also pi of c if you already have m dot C2, right? And the idea was, one of the assumptions we make is the turbine nozzle remain choked at design and over a wide range of the engine operating conditions. So what does this mean for the main equation of the m that we have already had? M dot 4. This one. Yeah. The nozzle at the face of the turbine remains choked. What does this mean from this equation? The Mach number of 4 would be 1. So that is going to change the m dot 4 equation that you already have we have already included the m dot C4, so we have already changed that equation to give us the corrected m dot. If you recall, m dot 4 was related to m dot C4 using the pressure ratios, that pressure correction and temperature correction. So if you plug those in and bring the area of the nozzle to the other side of the equation, this is what you're going to get. M dot C4 over A4 is going to be equal to the square root of gamma T over RT, the ratio between the pressure, reference pressure, and the square root of reference temperature, and gamma T plus 1 over 2 to the power of whatever, right? What is the variable in this equation? What is changing in this equation? Is it changing? Is the reference temperature changing at all? But these are reference values. This is not a pressure or temperature inside the engine. Right? This is a reference value that you choose. Right? You can choose whatever pressure. Why would that change?
If it's, so that's the choking condition?
We are going to have this equation because of this assumption. So we assume that we have the choked nozzle, which means that your end dot is 1. This is the equation you're going to get for m dot C4 divided by A4.
So if it's choked, the mass flow rate should change.
So you are saying this should change.
Yeah.
Okay.
So the area of the variable changes? Or
So these two, these n over A is the thing we are calculating, right? Using this equation, right? So this is like your y of a function, and I'm asking what are the independent variables here. This is a dependent. This really depends on whatever is changing here, right? So I'm asking whether anything is changing on the right hand side of the equation.
No, nothing's changed there.
Okay? Exactly. Nothing is changing here. So for a specific air, or for a specific gas, for which you have gamma T and R of T, you can actually, for a wide range of operating conditions, you can find a constant value for m dot C4 over A4. Does that make sense? So let's assume that the gamma of T is 1.33, which is usually the case, and R is 286.8, which is the case for air. Your m dot C4 over A4 is always going to be 227 kilograms per second.
What does that value help us to, like, what do we know?
This is going to help you a lot when we are going to see that in an example later on. This is a very important value when you're dealing with the performance math, right? Because so look at the performance math we have here. We have m dot C4 as a function of 1 over point T. So when you have that m dot C4 divided by A4 as a constant value, this is going to change. We can divide everything by A4, and this is going to simplify your performance. Does that make sense? But we will see that. We will see that. Yeah.
is the turbine nozzle almost always choked?
That's the assumption, right? That's the assumption that we usually make in this off-design analysis. The turbine nozzle is always choked over a wide range of operating conditions, right? So based on this relationship we have between m dot C2 and m dot C4, we can actually rewrite that equation. We can actually, not based on the original equation we already have for m dot, we can actually rewrite this equation and just plug in m dot Z2, mz2, and everything else. This is it. Based on these three equations, that's why I here. So we have this m dot equation for station 2, we have this m dot C4 over A4, right? And we have this relationship between m dot C4 and m dot C2, right? So based on these three equations, we can actually find the area ratio at the face of the turbine and the face of the compressor. Something that you have to keep in mind is that to find this area ratio, the value you want to use here is m dot C2 over A2, right? And m dot C4 over A4. So you shouldn't just use m dot C4 and then the C2, right? You have to calculate the C2 over A2 using this equation here, and you have to calculate the C4 over A4 using this equation, or you can just use this number, right? Why is that? But if you don't do that, if you calculate the C4 separately, the A2 and A2 here will cancel out. A4 and A4 here will cancel out. And this equation won't essentially solve for anything. Does it make sense? Okay. So this is the component matching for a regular gas generator. The next thing you want to talk about is the different types of gas generator or different types of nozzle. We usually deal with three specific different types of gas generators or jet engines, right? The regular one with only compressor, turbine, and the combustor, and the afterburning one with an included afterburner, as well as a turbofan, right? So these are the three main things that we deal with. So let's talk about this afterburner and see what is going to happen here. Okay. Usually when the afterburner is off in an afterburning engine, we usually call that condition the dry condition. Right? When afterburner is on, we usually call that condition the wet condition, which of course refers to the fact that you are adding fuel, and wet fuel, in the afterburner or not, right? Is there any question here before moving on? If no, it's the afterburning part of the analysis is actually pretty simple. So whatever you need to know is actually listed here, whatever kind of assumption we are making. But the main assumption we do make is that in the converted diversion nozzle, and this station 8 is always choked, right? That's the assumption we always make. If you write the equations, which I didn't include the equations, just the final conclusion from those equations. If you write those equations, this is what you're going to get. Your pi of t divided by the square root of tau of t for the turbine is going to be constant when the afterburner is off. You can actually make the same conclusion for the case where the afterburner is on. And we can find the ratio between the two areas. A8 is this area, is the choked area, divided by the engine face area. We can find that using this equation. And again, keep in mind that you have to find n dot corrected 8 divided by A8 in a separate equation, just like this whole value for this whole ratio here, right? If you were to calculate this area ratio. So the main actually takeaway from this analysis is the fact that pi of t divided by the square root of tau of t is constant for the both conditions. And we're going to see later on that we're going to see how it's going to help us. Is there any questions so far? So let's move on. Let's move on from the component matching, and let's talk a little bit about the off-design analysis. How should we really do the analysis? We have seen just a bunch of equations that were thrown at us, right? But here we want to get those equations together and figure out how we can use those ideas and those equations to do a real off-design analysis. The first thing, just as a reminder here, the first thing you need to know is the station numbers of each part of an engine from 0 to station 9, which is going to be your exit station for different engine analysis. And the non-parameters or the non-sets of design parameters are the design flight condition, the design compressor pressure ratio, the ideal heating value, the turbine inlet temperature, the design component efficiencies, design nozzle exit pressure, or the area ratio, and the gas properties, as well as the corrected mass flow rate, corrected shaft speed, and the actual Mach number at MT2. But these are the parameters that are very important in a design operating condition, design-based operating condition. What will become important to us when we are dealing with an off-design operating condition? Off-design flight condition, of course, is very important. Off-design turbine inlet temperature, and that's it, right? So we have 10 design operating conditions, 10 important parameters in design operating condition, and 2 important parameters in an off-design operating condition. But how can we relate the two? How can we use the concepts we have seen to do the analysis? Let's talk about the turbojet engine first, and then we'll go to the afterburning engine, and then afterwards we'll talk about the turbofan. Okay? So to do an off-design analysis of a turbojet engine, we will make some assumptions. The first assumption we'll make is that the turbine inlet is choked at both design and off-design operating conditions. The exhaust nozzle is also choked at both design and off-design operating conditions. And this equation is true, which we have already seen. The pi of t divided by the square root of tau of t is constant. Right? Okay. So the question I have for you guys before moving on is that did we have any relationship that related pi of t to tau of t from chapter 4? Where essentially you want to see if there is a relationship between pressure ratio and temperature ratio. We usually know the relationship if it was an isentropic process, right? But when it's not an isentropic process, we actually had this relationship. We had a very similar relationship. The only difference was the inclusion of the polytropic or small stage efficiency, right? That was the equation. So you can use this equation to this relationship and replace pi of t with tau of t and make a conclusion that the tau of t is going to remain constant. Okay. This is something I mentioned before, but I just elaborated on a little bit here. So for a wide range of operating conditions, your tau of t is going to remain constant. Okay. So how can we relate the design and off-design analysis? You already know how to do the design analysis, right? You already know the marching technique, all of those things, right? But how can you relate the two? The first thing you want to do is to find the tau of t from the design mode operation, right? Does it make sense? So essentially, you go back to your analysis. From the design analysis, you find the tau of t. Okay? And then the idea is tau of t remains constant for the design and off-design condition. So we're going to use the power balance between the compressor and the non-turbine. We're going to use the power balance between the compressor and turbine. Turbine here. And as well as the non-turbine expansion parameter, which is your tau of t, to do the off-design compressor, to do the off-design calculations and find the off-design compressor pressure ratio. Does that make sense? So essentially, this tau of t is going to be the linking part between the off-design and design analysis. You do the design analysis, you find tau of t, and then you're going to write the energy balance between the compressor and the turbine, and use this tau of t, which is going to be the same for the both conditions, and find the compressor pressure ratio, which is one of the goals usually in an off-design analysis. And using that, based on the equations we have already seen, we already know that the corrected mass flow rate is a function of the compressor pressure ratio, right? So using those, we can find the new corrected mass flow rate and shaft speed at off design. Is there any questions so far? No? I can see you're done with the class, but you have been done with the class from the beginning. So, okay. So based on what we saw here, how do you think we should deal with an afterburning turbojet engine? For an afterburning turbojet engine, of course we have the same phi of t divided by the square root of tau of t is going to remain constant for both of them. But something that you have to keep in mind is that although these are constant, both of them are constant, but they are not going to be the same constant. So they are different constants. Okay. Your design parameters, the linking part, which is going to be your tau of t, which is going to remain constant, and your off-design parameters. So the only thing that you really need to calculate here is the same as the previous case, which is going to be your pi of c. Is there any questions here? No? We can actually stop here, or we can cover these parts as well. Let's talk about this because this is pretty simple. Let's talk about the separate flow turbofan or the two-spool engines. We are going to make some assumptions, the same as before. We are going to assume the first nozzle choking station. Essentially, what we are assuming is that your high pressure nozzle, high pressure turbine nozzle, entering nozzle is choked, and the low pressure turbine entering nozzle, the nozzle at the face of it is also choked, right? And the exhaust, the convergent the station 8 is also choked, right? So the only thing that is being added here is the M18, which we are assuming is choked, and M4.1, which we are assuming is choked. Okay? So that's the only thing that is going to be different here. Again, we have the known design parameters. The only thing that is being added here is the design bypass ratio as well as the fan pressure ratio, which are the parameters you are already familiar with. And the off-design parameters are going to be this. But the thing that you want to calculate for an off-design parameter is going to be your compressor pressure ratio, your fan off-design pressure ratio, as well as your off-design bypass ratio. What is the general idea here? The general idea is actually exactly the same. For the low pressure turbine, this ratio remains constant for a wide range of conditions. This means that your pressure ratio is also constant. We can say the same thing for the high pressure ratio. Okay. And what can we get from the multiplication of the high pressure temperature ratio by the low pressure temperature ratio. What can we get from this multiplication? Tau T of H of tau T of L. Let's multiply them together. So this is the temperature ratio. That's TT. This one is TT 4.5 divided by TT 4, right? Multiplied by. Okay, so what did we get if we do that multiplication?
Temperature ratio of the whole turbine.
You're going to get the total turbine temperature ratio. That's it. So based on this, you can, of course, assume that your total turbine temperature ratio is going to be the same, constant. It's going to remain constant. We can also make another conclusion, which has a very lengthy proof. And I'm going to go over the proof here. Is that we can assume that the design bypass ratio multiplied by the high pressure compressor ratio multiplied by the square root of tau R, tau F divided by tau lambda is going to remain constant as well for the off-design parameters. So you're going to use these two constants. You're going to calculate these two parameters. You're going to use it design constant and make some calculations. There are some complexities when it comes to the separate flow turbofan that which we are going to discuss in the next lecture. And those complexities usually it essentially means that you have to do some sort of a trial and error when you're dealing with this type of a separate turbofan analysis. So I don't see. You may get in your take-home file exam, but you won't get any question as far as the trial and error goes in your quizzes or homework. So is there any questions so far?
Are we going to solve examples?
Yes. So I'm gonna finish this chapter on Wednesday, and we are going to start working on examples. Right? The thing is, for the rockets chapter, we need 3 lectures, right, with examples. So we are essentially, even if we dedicate the Monday that is coming in, the next week's Monday, even if we dedicate that Monday to solving examples, we won't be any behind. Sorry if my hand was interrupting the lecture. It's just these things happen, guys. I'm sorry about it. But let me know if you have any questions.